Hi all, I'm Nikitha and my teammates are Akhil and Nissi presenting you the two-dimensional fair queuing for multi-tenant cloud services research paper by the authors Jonathan Mace, Peter Bodik, Mandala Musuvathi, Rodrigo Fonseca, Krishnan Varadarajan. The problem addressed in this paper is fair queuing in multi-tenant cloud services, particularly focusing on the challenge of efficiently scheduling requests with the large variations in cost across multiple threads. This problem is of significant importance in the realm of cloud computing, where multiple users or tenants share resources and requests with varying resource requirements need to be efficiently scheduled to ensure fairness and optimal resource utilization. I believe this is an important problem in cloud computing environments where resource allocation and fairness are critical for providing satisfactory service to multiple users or tenants simultaneously. The authors have conveniently motivated this problem by highlighting the challenges associated with fair queuing in multi-tenant cloud services, especially in scenarios where requests have large variations in cost. The importance of the problem addressed in this paper is both theoretical and practical. Theoretically, it addressed uh, fundamental challenges in fair queuing algorithms, and practically, it has direct implications for real world cloud service providers. There are existing solutions for this fair queuing in multi-tenant cloud services like weighted fair queuing. However, these solutions have limitations that have their insufficient for addressing the significant challenges highlighted in the paper. The main limitations of existing solutions like weighted fair queuing are their inability to effectively handle scenarios with large variations in research, in request costs, and unpredictable workloads. The proposed solution is two-dimensional fair queuing. The two-dimensional fair queuing differs from the existing solution primarily in its approach to cost-based practicing and scheduling. Unlike the weighted fair queuing leverages a two-dimensional approach to efficiently schedule requests based on both predictable and unpredictable factors. The related work discussed in the paper provides a comprehensive overview of existing solutions in the field of fair queuing, highlighting their strengths and limitations compared to the proposed two-dimensional fair queuing solution. However, it's essentially to note that while the related work is discussed sufficiently, further research may be needed to explore other potential solutions and their applicability to different cloud computing scenarios. The two-dimensional fair queuing innovates upon fair queuing by introducing an additional dimension of fairness, extending its capability beyond traditional models. Its primary objective is to guarantee inequitable equitable bandwidth allocation, a task made more nuanced by factoring in flow significance or priority levels. The over The overarching aim of two-dimensional fair queuing is to engineer seamlessly schedules, particularly benefiting the tenants with the modest request size achieved through the minimization of burdeness, both temporarily and separably. So the there are two challenges noted here. The first one is high request cost variability. Request costs uh, in shared services exhibit wide variance spanning up to 4 orders of magnitude, impacting scheduling, and necessitating the spread of requests across different threads to achieve smoother schedules and prevent bustier behavior. The figure on the left shows the anonymized cost distribution for several different APIs in Azure Storage. The figure on the right-hand side shows cost distribution for several different tenants of Azure Storage. And the second challenge addressed is unknown request cost. Dynamic tenants with unpredictable request costs pose scheduling challenges, leading to busty schedules and impacting latency for other tenants, necessitating strategies to mitigate underestimation of cost and prioritize service for predictable tenants over unpredictable ones. The figure the figure on the left has several orders of magnitude between its 1% and 99% request cost. If we also condition of tenants, the figure of left the figure on the left shows most tenants using this API actually have very low costs, and the figure on the right shows the scattered plot of mean and coefficient of variation of request costs across many tenants and APIs. This figure shows time series for T2, T3, and T10, illustrating request rates and cost for the APIs being used. The figure A has a stable request rate, small requests, and little variation in request cost. The figure B, T3, stable with gradual changes, submits a large burst of requests. The figure C, T10, unstable tenant with frequent changes, is the most unpredictable tenant. The next presentation would be continued by my teammates.
Hello, now I'm continuing from where my friend Nikitha has been left. So, the main idea between the two-dimensional fake queuing 2DFQ. In this 2DFQ, it innovates. The authors have employed a comprehensive approach to demonstrate the effectiveness of their proposed two-dimensional fake queuing algorithm, encompassing theoretical analysis, prototype implementation, and simulations. The authors also provided a rigorous theoretical analysis of the 2DFQ algorithm, presenting mathematical proofs and performance guarantees to establish its correctness and efficiency. If we want to validate the practical feasibility of their solution, the authors implemented a prototype of the 2DFQ algorithm within a simulated cloud environment. This prototype served as a proof of concept implementation, which is allowing the authors to assess the real-world performance of 2DFQ. And additionally, they have conducted extensive simulations to evaluate the performance of 2DFQ across wide range of workload conditions and system parameters. And then they are likely performed multiple iterations of their experiments to ensure the robustness and consistency of their results. If we see here, it innovates upon fair queuing by introducing an additional dimensional fairness. But then traditional scheduling algorithms such as weighted fair queuing, WFQ struggle with this because they do not adequately handle the variability in request sizes, leading to inefficient resource allocation and potential service delays for smaller requests. And then the two-dimensional fair queuing is proposed as a solution to overcome the limitations of existing fair queuing methods. We're aiming to distribute requests of different costs across different threads to minimize the impact of large requests, blocking smaller ones, and maintaining a fair and efficient processing environment. And if we go to the next one. So the main idea behind the and the key components and the primary functionality of two-dimensional fair queuing system is, here we have the shared tenants A, B, C, D. The term shared tenants refers to the different clients or services that are operating concurrently within the same cloud computing environment. Each tenant represents an entity with its own set of requests that need to be processed by the cloud services infrastructure. And then if we are seeing at the worker threads, WO and W1, as per the research paper, these are the processing entities within the system. And out of these two specific worker threads, the notion of it resembles the notion of the worker threads. The threads WO and W1 are specified as the active components that execute tasks. Like in the context of cloud computing, these threads are responsible for processing the tenant requests. And then if we see the 2DFQ's distribution mechanism, the main functionality of the 2DFQ algorithm, which is to manage and distribute the incoming requests from the shared tenants across available worker threads. The distribution is designed to be optimized in such a way that it maximizes the resource utilization, making sure the computational power is used efficiently without idle time or wastage. So if we are seeing about the optimizing resource utilization, the aim here is to ensure that all resources are used to their maximum potential. This means like balancing the load. So uh, that no single thread is overwhelmed or underutilized, leading to a more efficient system. And if we see ensuring fairness among the shared tenants, the core objective of 2DFQ is to maintain fairness. The system should ensure each tenant gets equitable share of the computing resources, preventing preventing scenarios where single tenant could potentially consume more than its fair share, leading to resource starvation. So if the 2DFQ system does this by considering both the cost of the requests, how resource intensive they are, and the order of requests, distributing them across threads in a way that maintains a balance between servicing quick, less intensive requests and more substantial resource heavy requests. So this dual focuses on the efficiency and fairness, makes 2DFQ an advanced and equitable approach to request scheduling in multi-tenant environments. And if you see the differences or the comparison between WFQ and WF2Q scheduling comparison, 2DFQ, the diagrams or the charts comparing here are the execution timelines under WFQ. If we see W1 and W0, and the requested schedule produces under ODFQ W1 and W0, it illustrates how both scheduling algorithms allocate time to different requests. Like in WFQ, the requests are scheduled basically pure on their arrival and size without preemptive interruptions, leading to potential delays when large requests block the queue. And if we see WF2Q, like 2DFQ, the bursty nature of these two scheduling is highlighted, showing like significant variances in service rates for tenants due to this unmanaged large requests, leading to unfair resource allocation, where smaller tenants suffer more frequent and longer service interruptions. If we see the next slide, so if we see the multidimensional like implementation of 2DFQ, if we see the multi-dimensional scheduling, it introduces an innovative approach that considers the size and computational cost of the request in addition to traditional factors to schedule tasks. And the thread specific eligibility, the system assigns this eligibility times to requests based on their uh, traditional factors or based on the request of their size, effectively allowing like smaller size or the smaller tasks quicker access to some threads and scheduling larger tasks to avoid bottlenecks. So, and if we see efficient resource utilization, by distributing tasks across threads in this way, the StudioFQ is preventing large requests from monopolizing resources, leading to more efficient overall the system performance. And this method ensures that no tenants requests are delayed because of unduly nature, promoting like fairness in the processing of a mixed load of service requests. And if we see the known request cost, So there are like two. One is the expensive request and the production workload. If we see the performance of 2DFQ with the known cost, so if we see the performance metrics, this reviews the performance improvements brought by 2DFQ in scenarios where request costs are known. Like it details how 2DFQ reduces burstiness in service and provides like more stable and predictable service rates across all the tenants, especially benefiting those with like um, smaller and then less variable requests than compared with the larger ones. And if you see the quantitative improvements, the specific metrics such as this reduction in surveys or like lag variation in surveys and then enhanced fairness, these are the indicators that might be presented illustrating the effectiveness of TUDFQ in maintaining like the equitable resource distribution. Like they are like on a consistent thread. If we see the Gini and service lag and service received, so the specific metrics such as the reduction in surveys and the lag variation and enhanced fairness, these might be effective of the 2DFQ in maintaining equitable resource distribution. And if we see the unknown, if we have to address the unknown request cost with 2DFQ, like if we like an extension of 2DFQ is like introduced to handle unpredictability in requested costs, and if it incorporates pessimistic cost estimation techniques to for the services received, it incorporates pessimistic cost estimation techniques to manage the unpredictability inherent in some tenants' requests. So this is the extension for unpredictability. And if we look at the technical approach of unknown request cost of 2DFQ, this uses historical data and some worst case assumptions to estimate request costs, thereby minimizing the adverse effects of underestimations that lead to bursty schedules and then high latencies. If we see the cumulative frequency and the latency, so it is like historical, these are the historical data, these are the unpredictable ones. So if we see the service lag per tenant, it has to assume like worst case assumptions if you are making it, though estimate request cost minimizing the adverse effects of underestimations, and these are the bursty schedules, and the latencies are, if we can see, the latencies are very high and unpredictable. Now if we look at the experimental validation of the production workloads, the testing methodology would detail the setup for testing 2D FQE, likely like describing like how the simulated environment and a multi-tenant system with a mix of predictable and unpredictable request costs. Like this would involve varying the workload patterns and measuring how 2D FQE adapts to these changes. And the comparisons, if we see between the speed up and 2D FQE speed up and both, for if we see the both speed ups, this would include the benchmarks against the standard frequency like fair queuing algorithms such as WFQ and WF2Q. And here also we have to consider the metrics like latency, throughput, and queue length, which might be used to provide the quantitative measure of the performance. And the latency metrics, the data showing the latency.
Hello, this is Joshi, Naga, Venkata, Akhilesh, Yadav, Gooty. Here onwards, I will continue. Evaluation main result. Imagine a scenario where the cost of request is known. In such cases, 2D FQ shines by providing impeccable service of all tenants, irrespective of the complexity or the expensive of their requests. This means that even some tenants require resource-intensive tasks. 2D FQ ensure the fairness by catering to their needs without compromising the service of the quality of others. Now consider the flip side. When application costs are unknown and the unexpected requests are emerged, here 2D FQ continues to impress by delivering flawless service to predictable tenants. Despite the uncertainties surrounding application costs, 2D FQ maintains the consistency and the reliability ensuring that these tenants receive the resource they need without interruption. What's even more striking in the impact 2DFQ has a service lag variation and latency. For small and medium tenants, 2DFQ significantly reduces the service lag variation even in scenarios where request causes are known. This means smoother and predictable performance even at fluctuating workloads. And when requests are cost unknown, the benefits are even more pronounced. 2DFQ achieves a remarkable reduction in service lag variation, sometimes by orders of magnitude for the small and medium tenants. This translates to vastly improved user experience with faster responses time and minimal delays, even in the face of uncertainty. Moreover, 2DFQ does not just stop at reducing the service lag variation, it also tackles the tail latency with unparalleled efficiency. In increasing the unpredictable workloads, 2DFQ drastically improves the tail latency for the predictable tenants, sometimes by up to 100 times. This means that even in the most demanding scenarios, where outliers can distribute the performance, 2DFQ ensures that the vast majority of requests are served promptly and reliably. In real-world production-based experiments, the results speak for themselves. 2DFQ enhanced the 99 percentile latency by up to 198 times, showcasing its ability to deliver the consistent, high-performance outcomes in the most challenging environments. In summary, our evaluation of 2DFQ relieves its unmatched the capabilities in providing fair, reliable, and high performance of service tenants in the multi-tenant cloud environments. Whether it's known or unknown request calls, fluctuating the workloads or unpredictable scenarios, 2DFQ stands a beacon of efficiency and excellence ensures that all the tenants receive the quality of service by their deserve. Here we can see the three diagrams where I can clearly give clarity on that. Evaluation matrix. Here we can discuss about service lag variation, service rate, latency, Gini index. Firstly, we talk about service lag. First and foremost, which quantifies the disparity between service a tenant should be received under the generation processor sharing. We can call it a GPS model and the actual work done. Essentially, it measures how much delays tenants experience compared that what they ideally should receive. For intents, in a system which entrates and a processing rate of 4, we should establish a reference GPS system with a rate of NR to this lag accurately. Next, service lag variation. Building upon service lag, which captures the standard derivation of the service lag. This metric is crucial, particularly in the environments with booster schedules, as it is highlights the calculation in the service that can occur. High service variation indicates the interrupt performance, while lower variation signifies more consistent and predictable service delivery. Next, service rate. Another essential metric we consider is a service rate. The work done within 100 MES intervals. This provides a guaranteed insight into the efficiency and throughput out of the system. enabling to the how efficiency resources are utilized and allocated latency. In terms of user experience, we focus on latency, especially the 99 percentile latency, which measures the time between a request being encoded and completing the process. By concentrating the 99 percentile, we assumption the performance experience by the vast majority of users, capturing the outliers that may significantly impact the overall satisfaction. The last thing is Gini index. Additionally, a metric commonly used to access by scheduler fairness across all tenants. The index offers an snapshot of fairness, enabling how equability resources that are distributed among the tenants at any given moment. Orally, this comprehensive metrics we gain a understanding of 2D FQs performance across the variation dimensions, including the service delivery, resource utilization, latency, and the fairness. This horizontally evaluations enables us to access not only the aspects but also the impact of 2D FQ in enhancing all over the user experience, efficiency, the multi-tenant cloud environments. The final thing is conclusion. Like we can say, did the authors achieve what they set off to do? Is the paper well organized or presented? Or like we learn from what we learn from this paper? If in my opinion, for this, I want to conclude it. This paper effectively accomplishes its started objectives by introducing two-dimensional fair queuing algorithm, a novel solution aimed at tackling the infinity of problem resources accumulation in multi-tenant cloud environments. The authors organized this presentation starting with a clear delineation of the problem statement, followed by an in-depth discussion of exiting the solutions. In their like inquiries by methodologically the limitations of current approaches, the authors completely the motivate the need of new algorithm, thereby setting the stage for the introduction of two-dimensional fair querying. The organization and the presentation of the paper extremely with each section seamlessly flowing into the next, facilitating the comprehensive and the retention of the key concepts. The authors provide the comprehensive review of related work, ensuring the reader gains a throughout the understanding of the landscape within their proposed solution operates. This broad exploration of the prayer research not only the serves to the highlight of the novelty of their contribution, but also deeper appreciation for the challenges intended in the resources allocation of in cloud computing. The papers primarily contributed the two-dimensional fair querying algorithm is a significant advancement in the field, offering a two-dimensional approach to fair querying that address the shortcomings of the traditional methods. Um, through this theoretical analysis, the supplemented by the valuation through prototype implementation and simulations. The authors convincing the demonstrated the efficiency of 2D FQ in achieving improve the fairness and efficiency in the resource allocation. This multi-phase, this multi-phase validation approach not only enhance the credibility of the findings, but also provides the valuable insights into the implications of adopting 2D FQ in the real world cloud computing environments. And finally, what I want to say means overall the paper serves a valuable resource of researchers and participants alike, offering not only a novel solution to pressing the problem, but also a craft exploration of the broader implications and applications of the work. By combining theoretical with the practical relevance and presenting their findings in a clear and manner, the authors have made a significant contribution to a advancement of cloud computing research. It's truly remarkable uh, for us. Finally, thank you for everything. Thank you.